Good afternoon. I'm Gangwon from Moreh, and today I will talk about our cloud infrastructure software for hyperscale AI. First, I will introduce what our company is doing. So, Moreh is a software company developing AI infrastructure software. The AI infrastructure software means all software components between AI applications and underlying computing resources such as GPUs, TPUs, and NPUs. So AI is basically a large amount of computational work. So high performance computing resources and the software stack for them are the essential parts of AI systems. So the most known infrastructure software stack is maybe PyTorch and TensorFlow plus CUDA. And in case of Google's TPU, for another example, TensorFlow is working with XLA, TPU runtime, and driver. So there are many AI startups worldwide and in Korea, and most of them focus on AI-powered applications and MLOps solutions. On the other hand, we are focusing on the infrastructure software. So this is because we think that advances in AI technology over the past decade has been basically driven by the growing data and infrastructure. Of course, the AI technology itself has advanced a lot, but the foundation is data and infrastructure. So we believe that the innovation in AI infrastructure can make a huge impact on the entire AI industry. So as everybody knows, the era of hyperscale AI begins in around 2019 or 2020. For example, OpenAI's GPT-3 was released in 2020, and several large language models have been released within the last 3 years. Now people are expecting that larger and larger AI models can solve some problems that could not be solved before. The graph on the left shows the number of parameters of representative AI models in chronological order. So before 2018, the model parameters are usually on the order of hundreds of millions to few billions. But after 2019, the number of parameters started to increase rapidly. Note that the y-axis is log scale. So what has changed? In fact, the horizontal line on the left-hand side shows the model scale that can be trained within a single GPU. Now the model size is far beyond this scale. This means that now we must use multiple GPUs and GPU clusters to train the state-of-the-art AI models. So many companies and institutions are increasing their investment in GPU infrastructure. As the scale of AI infrastructure grows, several new challenges naturally arise. First, a GPU server itself is very expensive, and recently GPUs have a very long lead time. This is partially due to the global semiconductor shortage and also because the market is monopolized by NVIDIA. In addition, modern GPUs are consuming more and more power, so now it is almost impossible to install GPU servers in a usual office. And even data centers built with the old standard cannot accommodate GPU servers because of their power budget per rack. So securing a place to install GPU servers is another challenge. At this point, you might wonder if people are starting to use cloud services instead of building their own on-premise servers. But unfortunately, the use of the GPU cloud is still limited, and people prefer on-premise servers despite of many difficulties. So why? The main reason is that GPU cloud services are much more expensive than on-premise servers. Actually, I also have experiences of using a GPU cloud service, and after I used the service for just 4 months, it costs as much as buying a new GPU server. So then why this situation happens? Basically because they assign physical GPUs to a single user exclusively. This is due to the hardware level constraint of GPUs. So once users get a virtual machine, they have exclusive ownership of some GPU resources even while they are sleeping or on vacation. And they finally need to pay for GPUs according to the whole service time. This hurts the economics of GPU cloud services. And this is obviously very different from how the cloud provides other kinds of resources such as CPU cores and memory. And after the GPU cluster is built and running, one more hurdle remains. For training a large AI model on a GPU cluster, a user needs to manually split and parallelize each training job or training program. This is not trivial. This requires a deep understanding of underlying system architecture. Depending on the parallelization method, the efficiency and the overall training time may vary up to tens of times. This means that bad parallelization can make your 1,000 GPUs worse than just 100 GPUs. Moreover, whenever one of the hardware configuration, model structure, or target dataset changes, the optimal parallelization scheme also changes. You need to repeat all low-level parallelization and optimization tasks every time. So we believe that many infrastructure level challenges of the current AI industry is basically the problem of existing infrastructure software stack. Because of the software components that are mainly used today, for example, PyTorch and TensorFlow were designed and created before the hyperscale AI era. So our goal is to redesign and re-implement the entire software stack to fundamentally solve the problems of large-scale clusters and clouds. So our software features accelerator portability, single-device abstraction, and application-level virtualization to lower the cost of building AI infrastructure and to enable scalable and flexible use of accelerators. At the same time, our key design goal is to provide 100% PyTorch and TensorFlow compatibility and to ensure the same user experience as traditional software stacks. This is practically very important because there are some approaches to solve the same problems by proposing a completely new API, but users will not accept that kind of technology because a huge AI ecosystem is already built on top of the legacy software. So this is the software stack what we are developing. So we provide a complete alternative of existing PyTorch, TensorFlow, and CUDA. It aims to support various types of accelerators, including non-NVIDIA GPUs and NPUs. In addition, it has a new component called Moreh AI compiler to manipulate applications workload and to automatically apply many optimizations. So I will not cover too many technical details in this presentation, but one of the core technologies of our software is runtime IR construction. It internally records the behavior of an application as a computational graph, and based on this bird's eye view of what users want to do, it can apply many compiler techniques. And we introduced a graph-level compiler called Moreh AI compiler to execute user applications in an efficient way without any user intervention. All the compilation process is completely hidden from users. One of the major features of our software is to encapsulate a large cluster as a single device. So users just need to write down a program targeting a single device. They do not need to consider parallelization across multiple GPUs and multiple nodes. Then data and computation are automatically distributed to the GPUs by our software. Moreover, we can even support heterogeneous GPUs in the cluster. For example, you may buy some A100 GPUs in this year and buy newer H100 GPUs in the next year. And maybe you may adopt the new GPU architecture in the next year. Then our software can encapsulate these different accelerators into a single device and decide the optimal parallelization method by considering the performance of different accelerators. We have been cooperating with KT to apply this technique to KT's Korean language model training and to develop various large-scale AI models in a timely manner. Another feature of our software is application-level virtualization. So we do not expose physical accelerators directly to users. Instead, we provide a virtual GPU to users. Our software manages the mapping between virtual GPUs and physical GPUs. So this enables GPU dynamic allocation, one-to-N and N-to-1 mapping between virtual and physical GPUs, and live migration for fault tolerance. Especially the dynamic allocation enables more flexible GPU cloud services and dramatically improves the average utilization of cloud GPUs. We call this technology application level virtualization because it is implemented in the AI framework level and not the hardware or driver level technology. Existing hardware level GPU virtualization such as NVIDIA Grid incurs significant overhead. However, this technology is very lightweight and can be practically applied to real-world GPU cloud services. Based on our software stack, KT Cloud has released a new GPU cloud service named Hyperscale AI Computing. So this service is a kind of IaaS, infrastructure as a service. So it provides a virtual machine and a virtual GPU named KT AI Accelerator inside here. This virtual GPU is powered by Moreh software and acts as a user NVIDIA GPU. So users can execute existing PyTorch and TensorFlow applications on this virtual GPU. Users can choose one of the flavors of the virtual GPU from small, medium, large, X-large to 48 X-large. So this flavor decides how many physical GPUs will be allocated when the user performs something on the virtual GPU. For example, if the current flavor is 2x large, then 8 GPUs will be allocated. The physical GPUs are located in the remote servers, and our software manages interactions between applications and these GPUs. The Hyperscale AI Computing service highlights several features like this. So it provides the pay-as-you-go pricing model for GPUs because users actually occupy physical GPUs in this manner. And we expect that this pricing model can reduce the effective price of the GPU cloud by 70%. Users can easily scale up the amount of computing resources up to hundreds of GPUs by switching the virtual GPU flavor. And as I mentioned before, users can easily utilize multiple physical GPUs with the help of our compiler. So in conclusion, we are cooperating with KT to solve many problems in cloud services and AI model development by infrastructure level software technologies. And we believe that the Moreh platform will be the new standard for hyperscale AI. Thank you for listening.